Okay, I want you to look at this proposition here. It says, if n is a natural number, then 1 plus negative 1 to the n times 2n minus 1 is a multiple of 4. Let's think about how we would prove that. Okay, so n is a natural number. Now, look at this part. Negative 1 to the n. What do you know about that? Isn't that always going to be either 1 or negative 1? And that's the only thing that that part accomplishes, right? Negative 1 to the n only accomplishes one thing, which is to make this be multiplied times 1 or negative 1. And what makes the difference between negative 1 to the n being 1 or negative 1? It's 1 if n is even, and it's negative 1 if n is odd, right? So you see you have here a dichotomy. There's two different paths to go down, and they're going to be very different depending on which path you go down. So in a situation like that, it's very common to say, all right, I'm going to handle both paths separately. So I will prove that if n is even, then this is a multiple of 4. And then I will prove if n is odd, then this is a multiple of 4. Okay? Because they probably will look very different. I mean, if you can do both of those at once, then even better, more power to you. But they will probably look very different, because in one case, this will be 1, and in another case, it'll be negative 1. So they probably look very different, and that's why I'm going to think about doing them separately. Okay, and that's what we call a proof by cases. So let me show you how you can do that. So let's start out by saying, let n be a natural number. Okay. Then, what do I know? I know n is even, or n is odd. Okay, and then I'm going to do those separately. Okay, I'm going to write, I'll even put a space in there. You don't have to, but I'll do that. It might help keep things organized in your head. So let's do suppose n is even. Okay, and from now on, for me, n is an even number, and I'm going to show that this is a multiple of 4. Okay, and then I'll do the case where n is odd. All right, so, whoops, I wrote suppose is even. That doesn't make any sense. Okay, suppose n is even. All right, so remember what you want to show. You want to show that this is a multiple of 4, so I'm hoping that that will equal 4 times an integer. All right, what do I have to go on? Well, n is even, so that tells me something about n, which I should write down, and it also tells me something about negative 1 to the n. Okay, so let's write these down here. So then What does it mean to be even? Remember, it means 2 times an integer. So when I write suppose n is even, then I can write then n equals 2 times something, I'll call it k, where, what is k? K is an integer. Okay, I also know that -1 to the n equals 1. We can write that as in the next line. Okay, or let me point this out to you. Both of these, those are both because of one thing. Because n is even, right? So it makes sense. I'm not saying this is better or worse. I'm just telling you that you can certainly do this. You can certainly put them together because they are both because n is even. So rather than writing them as 2 separate lines, it also makes a lot of sense to just say then n equals 2k, where k is an integer, and -1 to the n equals 1. Because those are both because of this. So it makes sense to point them out together. Okay? All right, so let's see what that number would look like. Hence, 1 plus -1 to the n times 2n minus 1 will equal what? It'll equal 1 plus 1 times 2 times 2k minus 1, which equals, what does that equal? Now this is just basic algebra, so go ahead and just work that whole thing out. Okay, a 9th grader can do that, so you don't have to show, oh, I'm going to distribute the 1 and things. So you don't have to show stuff like that. This is in 9th grade. So go ahead and work that out and see what you get. Did you get 4k? That's what you should get. Okay. Is 4k a multiple of 4? It sure is. It's 4 times something. And what kind of thing is the something? It's an integer. And so that is what we call a multiple of 4. So therefore, 1 plus -1 to the n times 2n minus 1 is a multiple of 4. Is it important that k was an integer? Yes, it was, because 4 times 1/3 isn't a multiple of 4. Do I need to point out that k is an integer? Well, not here, because I already have pointed it out there. It is important to point it out, but I don't have to point it out a second time. Okay? All right, so that takes care of the case where n is even. A lot of times people will even write case 1. That is not mandatory, just so that you know. It's not mandatory, but it's helpful. It helps the reader follow along with what you're doing. But it's not mandatory to write case 1. Okay? All right, what would be case 2? Case 2 is where n is odd, so let's write suppose n is odd. Okay, now, just so that you know, if you were to write here case 1, then you would write here case 2, and you would say suppose n is odd. Now, here's what I like to do. If you don't write case 1, case 2, then in that case, that's not, no pun intended there, but in that case, my suggestion is that when you do the second one, you write suppose, comma, on the other hand, misspelled it, comma, that n is odd. So what that does is it's just a second way of alerting the reader. When you say on the other hand, you're saying, hey reader, by the way, I'm not just continuing still with the same situation that n is even. I'm actually doing a different situation here. So that phrase, on the other hand, that is a key to the reader of, we are now switching to the other case. You see what I'm saying? I also think it makes your proof sound a little bit more sophisticated, if that matters to you. Now, sometimes when you do proof by cases, one case will differ greatly from another, but in this case, it doesn't. The skeleton of the proof is the same. A couple of the details work out differently because of n being odd instead of even, but the idea is going to be exactly the same. We got a line like this written down. We will then write down what it means for n to be odd, and this will be a negative one instead of a positive one. And then we will substitute that in for n and work it out. And we will end up again with 4 times something. And we'll make our conclusion, okay? It'll be the same exact pattern. Okay, so suppose on the other hand n is odd. Then n equals, what's an odd number look like? It's 2 times an integer plus 1. So I'm going to write 2k plus 1, where k is an integer. And also, what else? Negative 1 to the n will equal negative 1. Now let me ask you a question. Is it okay to use the letter k here? I've already used it up here. Well, the answer is yes, it is okay. If it makes you uncomfortable, then don't do it. Choose a different letter. But it is okay, and here's the reason why. Because this is like a sub-proof. It's a proof within a proof. Case 1 is. So case 1 stands by itself. Case 2 is totally separate from case 1. But the important thing is that case 1 ended here. Whoops, sorry. Case 1 ended here. So k was being spoken for. But now that has ended. K has been released back into the alphabet again. Okay? And so you can certainly pick k again here in this, which is a separate proof within a proof. Okay? But bottom line is, if that makes you uncomfortable, then you can choose a different letter. Okay. So there we are. And then what will I write next? I'll write hence 1 plus negative 1 to the n times 2n minus 1 will equal 1 plus negative 1 times 2 times 2k plus 1 minus 1. And again, that's just basic algebra, so go ahead and work it all out. See what you get. Okay, you should get negative 4k, which equals 4 times what? Because remember, what's our goal? Our goal is to show that it is a multiple of 4. So you should really end off with 4 times something. So I say it's best to not stop at negative 4k. I believe it's better to then say, which equals 4 times negative k. Okay? Therefore, 1 plus negative 1 to the n times 2n minus 1 is a multiple of 4. Now, I want to say just a couple of last minute things about this. Why is it a multiple of 4? Because here I have that it equals 4 times what kind of number? 4 times an integer. Have I pointed out yet that negative k is an integer? Technically, no. I said that k is an integer, but I didn't say that negative k is. So, to cover those bases, how would I do that? I would say where negative k is an integer. Why is negative k an integer? Because k is an integer, and the opposite of an integer is an integer. Now, just to give you an insight into my own thinking, I would not say that the proof was deficient if you left this off. This is just my own thinking, okay? If you have said that k is an integer, I would not require somebody to then point out that negative k is an integer. I just kind of think those go hand in hand. Now, if it was something like 5 minus k, then I would think that you should point out that that's an integer. Okay, but let's not get off into the weeds. I have it written there. It's good to write it there. Let's just leave it at that. Okay, I didn't do that up here. I just want to remind you, I didn't do that up there. Why? Because it's 4 times k, and I already said k is an integer. Down here, it's 4 times negative k, and I had not previously said that negative k is an integer, and so that's why I'm pointing it out. Because to be a multiple of 4 means 4 times an integer. So you have to show that it's 4 times something, and you also have to show that the something is an integer. Okay? Now, some people like to then tie up the cases together. It's kind of like you're in a Zoom meeting here, and then you break up into the breakup rooms, and then you come back together again. If you want to do that, you would say, thus, in either case, (1 plus negative 1 to the n times 2n plus 1 is a multiple of 4. Is that last part necessary? No, but it is nice. So you decide. I'll leave that up to you. Okay. Technically, my job was to show that that number is a multiple of 4. And what did I show? I showed that n is one of 2 things. And I showed that in both cases, the number they were asked about is a multiple of 4, and so I showed what I needed to show. I don't have to go any further after that. But once again, it is nice to just wrap that up and have some nice closure. I just want to make sure you understand that that last line is not mandatory, okay? All right, so there we go. That's the end of that proposition. Let's do another one. This is very similar. It says every multiple of 4 equals 1 plus negative 1 to the n times 2n plus 1 for some natural number n. Okay, let's prove that. Okay, notice that they did not give us the name of something specific to work with. They gave us a description, right? They said every multiple of 4 equals this form. So we are supposed to work with multiples of 4, right? But they didn't give us a name to use. So we need to do that ourselves. So we will start with let k be a multiple of 4. Now I have something specific to work with. Okay? So what does it mean to be a multiple of 4? It means it equals 4 times an integer, right? Okay, so then k equals 4 times something. What letter do you want to use? The book uses an A, so let's just do that, okay? Where A is what kind of number? Actually, is it okay if we don't use A? And I'll tell you why. Because sometimes it just feels weird because there's A right there, but that's something totally different, right? Here it's a number, and here it's an article. And that feels awkward to me. So how about, can we use M instead? I don't want to use N, okay? Because I'm reserving that for, hopefully we're going to show that 4m equals something like this. And whatever ends up being in that spot right there, I'm going to call n. So I'm saving that name for later. Okay, so let k be a multiple of 4. Then k equals 4m, where, what else do I need to say? Where m is an integer. Okay. All right, now we're going to do this by cases too. And I think that brings up two questions. Number one is, what are the different cases going to be? But another one is, it's not obvious here that we need to break this up into cases. So how would you know that? Okay. I can't always answer questions like that for you. I can't always say, you will know when to do this whenever you see that. Some of that's not answerable because I can't explain to you every situation that you're ever going to see in your life. Okay, so some of it just is going to take some experience. Okay, but let me try to explain a little bit of why are we going to do this in different cases. Well, do you have any idea right now how you would get 4m to equal 1 times -1 to some power times 2 to whatever that power was plus 1? There's no connection at all between those two things. That's obvious, is there? So that's where you start to say, well, maybe I can break this up into some different possibilities. Okay? And it might be true that we should do the even-odd separation, or maybe not. Maybe we should separate the possibilities in some other way. Okay, first of all, I see that I made an error here. Sorry, I'm not sure what I said out loud, but I see that I wrote 2n plus 1. Either way, no matter what it is I said, it was supposed to be 2n minus 1 all along. So let's fix that. And now, let's think for a minute. Okay. So, where have we left off? K equals 4m, where m is an integer. All right, now, this one's a little bit harder. I would point out this. We're trying to get 4m to equal something of this form. And I don't know what n is going to equal. See, now this is important for you to understand. We need to find what n needs to be, because it says for some n. So we need to find an n, okay? So I don't know what n equals. I'm trying to figure that out. But I will still say this, which is similar to what I said in the last example. This part right here still depends a lot on whether n is what? Even or odd. So here's what I'm going to do. I'm going to work my way backwards a little bit. I'm going to say, all right, I don't know what n looks like yet. Maybe it can't be even. But nonetheless, let's just say that if n comes out to be even, then in order for 4m to equal 1 plus negative 1 to the n, oh, sorry, again, that should have been minus. So let me say that again. If n is even, then in order for 4m to equal 1 plus negative 1 to the n times 2n minus 1, then 4m would have to equal 1 plus 2n minus 1, right? Why is that? It's because negative 1 to the n would just be 1, which would mean 4m would have to equal 2n, right? Which means n would have to equal 2m. So here's what I'm saying. So it looks like, oh, I found n, right? And we did, but let's go through this, okay? We're saying if n is even, and if 4m equals that stuff on the right, then n would have to be 2m. So I worked my way backwards, figuring out what n would have to be in order for 4m to equal this. Okay, now one thing to point out, first of all, I want to make sure that that actually works in the other direction, because I want to say if 4m equals this, then what does n have to be? Okay, and that's fine, that's not going to be a problem, but here's another thing that I do have to be a little bit more concerned about. N has to be a natural number. If n ends up needing to equal 2m, and n has to be a natural number, then remember m is an integer, so there's a restriction that's going to be placed on m in order for 2m to be a natural number. Now, 2 times an integer is always an integer, but 2 times an integer is not always natural, because what's the second thing that I know about natural numbers? They're integers, yes, but they're also what? They're also positive. So for n to equal 2m and be a natural number, 2m would have to be positive, which means m would have to be what? would have to be positive. So this only works if m is positive. Okay? All right, let's leave that for a minute. Even if you still feel a little bit lost or something, let's just leave it for a minute. Let's say, what if n came out to be odd? In that case, 4m equals 1 plus negative 1 to the n times 2n minus 1 only if 4m equals 1 plus negative 1 times 2n minus 1, which would mean 4m would be equaling what? 2 minus 2n, right? Which would mean that 4m minus 2 would equal negative 2n, which would mean that n would have to equal what? 1 minus 2m, correct? But again, remember, our n is supposed to be a natural number, which means it's supposed to be even. Sorry, I didn't mean to say even at all. I meant to say positive. So 1 minus 2m would have to be positive. Which means 1 would have to be bigger than 2m. Which means m would have to be less than a half. What integers are less than a half? Well, the integers that are less than a half are the integers that are 0 or less. So this up here only works if m is equal to or less than 0. I see over on the left I wrote the word and instead of if. Let me fix that. Okay. So what we have here is we have two cases. We are going to end up separating into two cases. One, and is m is positive, and the other case will be m is non-positive. That's going to be our two cases. And if m is positive, then we're going to say let n be 2m, which is even. So this will be true, so this will be true, so this will be true. We'll be going in the other direction, you see. And then we'll say the other case will be m is non-positive, which means 0 or negative. We'll say let n equal this, then this will be true, then this will be true, then this will be true, then this will be true. Okay? That's how it's going to work. So here's our two cases. Now the book separates it into three cases. It does m equals 0, m is less than 0, and m is greater than 0. Why did they do that? I have no idea, because it's entirely unnecessary. Because these two cases, there's no reason whatsoever that they can't be done together. Okay? So let's write it out now that we have a plan. Okay, so let k be a multiple of 4, then k equals 4m, where m is an integer. Okay, let me get some space here. All right. If m is greater than 0, I think I would prefer the word suppose. Here, let's do it like this. Suppose m is greater than 0. Let n equal 2m. Then n is a natural number. Oops, I almost wrote integer. Okay. And one plus negative 1 to the n times 2n minus 1 would equal 1 plus 1 times 2 times 2m minus 1, which would equal 1 plus 4m minus 1, which is 4m. Done with that case. Okay, and then I'll do the other case. Suppose, on the other hand, that m is equal to or less than 0. Let n, in this case, equal 1 minus 2m. Then n is a natural number, and 1 plus negative 1 to the n times 2n minus 1 would equal 1 plus negative 1 times 2 times 1 minus 2m minus 1, which would equal 1 minus 1 minus 4m, which equals 4m. And we're done. One thing I want you to notice from here is that your scratch work is not your proof. You do scratch work to figure out how the math needs to work out. And writing your proof is separate from that. Okay, and there you go. That's the whole proof. Okay. Okay, now, those two examples are in the book in section 4.4. We're going to move right on into the examples that are in section 4.5. Okay, I'm going to show you something that we can sometimes do, and it's going to feel like cheating, but it's not. So I want to write this down. If two integers have opposite parity, then their sum is odd. Parity means even odd. Okay, This is really easy to prove, but we're doing it because I want to show you something very particular, okay? So let's prove this. All right, so let's say we're going to start with two integers, right? So let x and y be integers. Okay, and I want to say suppose they have opposite parity. So how many ways can that happen? You could say, well, only one way, and that is if one of them's even and the other's odd. Okay, that's true, but use the names that we've written down. Use x and y. So isn't there two ways that they can have opposite parity? One is x even, y odd, and the other is x odd, y even, right? So let's write that down. So what I want you to see is that you see there's actually two cases here. So the first case is suppose x is even and y is odd. Okay, all right, now let's go with that. Then x equals 2k for some integer k, and y equals 2j plus 1 for some integer j. So let's write this down. Then x equals 2k and y equals 2j plus 1 for some integers k and j. Okay? Hence, what will their sum look like? Their sum will equal 2k plus 2j plus 1, which, by the way, notice is the same thing as 2 times k plus j plus 1, which if we call that number k plus j, what do you want to call it? Let's say n, okay, which equals 2n plus 1, where n would be equaling what? Where n would be equaling k plus j. What kind of number would that be? K and j are integers, so k plus j would be an integer. So I've shown that x plus y equals 2 times something plus 1, where that something is an integer. Isn't that the definition of being odd? So I have just shown that x plus y would be odd. So in the case that x is even and y is odd, then x plus y comes out to be odd. What's the other case? Do you remember? The other case is supposing that. So what's the other possibility? X is odd and y is even, right? Or let's say this. Y is even and x is odd. So all I did was I just took the letters x and y and just swapped them, right? There's only difference. Which means everything else is going to be the same except just the letters x and y switched. So we'll have then y equals 2k and x equals 2j plus 1 for some integers k and j. Oops, I forgot my comma. Hence, their sum. I can even write y plus x if you want, that's fine. Would equal what? It would equal 2k plus 2j plus 1, which equals 2 times k plus j plus 1, which equals 2n plus 1, where n equals k plus j, which is an integer. Thus, x plus y is odd. Okay, now, there we go. It's very good proof. We did a proof by cases. It's perfect, okay? But here's what I want to point out. I want you to examine this case and compare it to this one, okay? And do you notice that they are literally, and I literally mean literally, okay? They are literally the same thing, except with the names of the numbers switched, right? Other than that, just the names switched. They are literally the same. So that means that they are mathematically the same. They are the situation of one number's even and the other number's odd. They are mathematically identical. There is a difference, but it's not a mathematical difference. It is only a naming difference. Which number did you call the even one and which did you call the odd one? So, because of that, it is not necessary to write out both cases. What we can do is this. Give me a second here. Okay, what we can do, I shrunk it down so I can fit. I didn't want to erase what we had already written, but over here, let's say, so where it says suppose x is even and y is odd, I'm going to throw in a phrase there which sounds like I'm cheating. I'm going to say suppose, oh, I should write it in black really. So suppose, comma, without loss of generality, comma, x is even and y is odd. What's that mean, without loss of generality? It's saying, look, I'm going to call one number even and the other odd. It doesn't matter which is which. I'm going to pick x for the even number and y for the odd number. But see, here's the thing. Again, I'm not really picking, I'm not really saying I am saying let x be even and y be odd. But what I'm really saying is one's going to be even and the other's odd. Let's call the even one x and call the odd one y. That's basically what's happening here, you see. And without loss of generality means that there's another possibility, right? And the other possibility is y is even and x is odd. But the only difference there is a difference of naming, not a mathematical difference. And so therefore, by just looking at this one case, we do not lose any generality. Okay? I hope that makes sense. You can only use that phrase without loss of generality and then do one case and have it count for two cases. You can only do that if the only difference between cases is a naming difference. Okay? And furthermore, when you're reading a proof and you see that without loss of generality, the proof writer is telling you that there is another case, and the only difference in that case would be switching some names. And so you should think to yourself, okay, so what would be the other possibility? So when you're reading this proof, when you see let x and y be integers, and then you see suppose without loss of generality that x is even and y is odd, then in your mind you should be thinking, okay, so that means there's also the possibility that y would be even and x be odd, and that proof would look mathematically identical to this one if I just erased every x and replaced it with a y, and erased every y and replaced it with an x. Okay? And one last thing to say is without loss of generality is oftentimes abbreviated as WL. Oh, my pencil just stopped. There we go. WL. Hold on a second. My pen's not working. Well, it's not working, so let me just say it. WLOG. Okay, you probably guessed by now that that's the abbreviation for without loss of generality. Okay. There's another example in the book, but it's almost identical. I don't think it's necessary for us to go through that one as well. It's also two integers of opposite parity, so it's exactly the same situation. Oh, I'm sorry. I'm looking at it a little closer now. It's not. It's the same one. It's the same proposition. They've done it in the book this way, and then they did the same proposition again this way. Okay, so exactly what we've done here in the lecture, they've done in the book. They used m and n instead of x and y. So that's a very useful tool, this idea of without loss of generality. It's very useful. Okay, but remember, you can only use that when the difference between cases is simply a naming difference. Okay, not a mathematical one. If there's any difference in the mathematics, you are not allowed to say, well, it's pretty much the same, so I'm just going to say without loss of generality, the other case is the same. No, that is not allowable if there is any mathematical difference at all. Okay? All right, so that takes us through section 4.5, and that ends chapter 4. We'll start chapter 5 in our next lecture.